Hello, welcome back everyone. Today's lecture is on the first law of thermodynamics for open systems. This is work that I did together with my dear friend and colleague, Professor Long-Ching Chen, who is also a professor of material science and engineering here at Penn State University. We have a paper that is published on this topic. It's called On the First Law of Thermodynamics for Open Systems, which has just been published in MRS Bulletin. Also, you can find more information on Professor Chen's textbook, Thermodynamic Equilibrium and Stability of Materials. If you're looking to learn more about the thermodynamics of materials, this is really the best book to go for. So let's dive in. Now, when we are studying thermodynamics, typically we need to define the system that is under study. The system is that part of the universe that we care about for our particular scientific experiment, and that system has some internal energy associated with it, which is typically given by this capital U. Now, surrounding the system, we have our surroundings. The surroundings have an internal energy associated with them, labeled here as U with this subscript surroundings. Together, the system and the surroundings make up the universe, and therefore the total internal energy of the universe is simply equal to the internal energy of the system plus the internal energy of the surroundings. So the system is what we want to study. The surroundings are everything else in the universe that is outside of the system, and then the universe is everything together, the system plus the surroundings. And the first law of thermodynamics at its most fundamental level is just a statement of the conservation of energy of the universe. So the first law states that the energy of the universe is a constant. In other words, U total, the internal energy of the universe, is equal to the internal energy of the system plus the internal energy of the surroundings, and that total is a constant. So energy can change forms, energy can move between the system and the surroundings, but the total amount of energy in the universe must always be a constant. Now, within the field of thermodynamics, there is a traditional form of the first law, which is probably the form that you would see as an undergraduate student in most introductory textbooks. And normally, this traditional form of the first law says that the change of the internal energy of your system is equal to Q minus W, where this delta U here is the change in internal energy of the system. Q is the heat transfer into the system. So in other words, the heat that is leaving the surroundings and going into the system, minus then the capital W, which is the work performed by the system. Now, in more recent textbooks, there is another way of expressing the same thing, where the sign of the work changes from a minus W to a plus W. And that is because if we use the plus W, we're changing the perspective of whether the work is being performed by the system or the work being performed on the system. If it is a minus W, this is work performed by the system. But if the sign changes so that it's Q plus W, this is work that's being performed on the system by the surroundings. So in many of the more recent textbooks, you'll see the first law expressed this way. Now, in this particular lecture, we are concerned with the first law of thermodynamics for open systems. Open systems are where we have transfer of chemical matter between the surroundings and the system, and that's not accounted for in this particular form of the first law. And so what I would like to do is to go into more details about how we derive the first law of thermodynamics for open systems, and also do it in a more intuitive fashion compared to what is given here in between heat and work. Now, in order to do this, we need to consider a simple system here that has three contributions to its internal energy. And with these three contributions, we can write that the total internal energy of the system is equal to the thermal energy, so this is U sub T, plus the mechanical energy, U sub M, plus the chemical energy, U sub C. So three different contributions to the internal energy, and if we add them all up, we get the total internal energy of the system. Now, in addition to these energies, we need to consider the types of matter that carry those energies. And for this simple system with three different types of energies, there are three different corresponding types of matter that carry those energies. When it comes to thermal energy, the corresponding thermal matter is the entropy, which is denoted S. For mechanical energy, the corresponding type of matter is the volume, V. And for chemical matter, the amount of species, the N number of moles of the chemical species is the amount of chemical matter that carries the chemical energy. So we have three types of energy, thermal, mechanical, and chemical, and three corresponding types of matter, the entropy S, the volume V, and the number of moles of chemical species, which is given by N. Now, the other important concept that we need to introduce is that of a thermodynamic potential. Any type of potential is defined as being the amount of energy divided by the amount of matter that is carrying that energy. So it's divided by the corresponding amount of matter. So, for example, the thermal potential would be equal to the amount of thermal energy divided by the amount of thermal matter carrying that energy. So in other words, the amount of thermal energy here is U sub T, and the amount of thermal matter is the entropy. So the thermal potential is just the thermal energy divided by the thermal matter, and that is something that we know and love as just the temperature of the system. This is what you measure with a thermometer, and what this is giving you is the amount of thermal energy per the amount of thermal matter. And one of the interesting things about potentials, like this thermal potential, is that because it's a ratio of two extensive quantities, what you get is an intensive quantity. So the thermal energy is extensive, meaning that the amount of thermal energy increases with the size of the system. Likewise, the amount of thermal matter is extensive. That also increases proportionally with the size of the system. And so if you take the quotient between those two by dividing them, what you get is an intensive quantity, the potential, in this case, temperature. So this is what we get for the thermal potential. If we move on to the mechanical potential is the amount of mechanical energy divided by the amount of mechanical matter. And that ratio, therefore, is this U sub m. This is the internal energy from the mechanical source, divided by the amount of mechanical matter, which is the volume of the system. And that ratio, that mechanical potential, is just the negative of the pressure of the system. Pressure, of course, being an intensive quantity. The minus sign is here just based on the definition of pressure, which is normally defined as being something that's compressive rather than tensile. And for that reason, we pick up a minus sign here for the mechanical potential. Lastly, we have the chemical potential. The chemical potential is simply the amount of chemical energy divided by the amount of chemical matter. This is U sub C divided by N, the number of moles of the chemical species. And that ratio is simply the chemical potential, which is usually denoted by the Greek letter mu. So we've got three different types of energies, three different corresponding types of matter, and three different corresponding potentials. The thermal potential, which is the temperature, the mechanical potential, which is the negative of the pressure, and then the chemical potential given by mu. And so now if we use these equations here, we can consider the total internal energy of the system, U. It's equal to the summation of the thermal contribution, the mechanical contribution, and the chemical contribution of the internal energies. And using these equations then, we can write the thermal energy here, UT, as equal to T times S. So if you take this equation, multiply by the entropy, you get that the thermal energy is equal to the temperature of the system times the entropy. In other words, the amount of energy that you have is equal to the potential times the amount of matter. And so we can write the thermal internal energy as simply Ts. the temperature of the system times the entropy. The next term is the mechanical energy. To get the mechanical energy, we take the second equation and multiply both sides by the volume. And what we get is that the mechanical energy is equal to minus PV. It's equal to minus the pressure times the volume. And so we can write that second term as minus PV. The last term is the chemical energy. To get the chemical energy, we take this third equation and multiply both sides by N, the number of moles. And what we get is that the chemical energy is equal to the chemical potential times N. So this last term becomes mu N. So now this total internal energy of the system can be written as Ts minus PV plus mu N. So temperature times entropy minus pressure times volume plus chemical potential times number of moles. Now let's consider then this equation here for internal energy. This is the same equation from the previous slide. How do we get the Gibbs free energy from this? What we can do is rearrange the terms such that we solve for this mu times n. If we solve for mu times n, what we need to do is subtract Ts from both sides of the equation. That gives us this minus Ts here. And then add PV to both sides of the equation, which gives us this plus PV. So simple algebraic manipulation shows that mu times n is equal to U plus PV minus Ts. And of course, this from the previous slide, mu times n, is also equal to the chemical energy of the system. And this, you'll probably note by this equation, is also equal to the Gibbs free energy of the system. So this is showing that the Gibbs free energy is just another name for the chemical energy of the system, and the Gibbs free energy is simply given by the chemical potential of the system times the number of moles of the chemical species. And we can write this out as the internal energy plus the PV contribution minus the Ts contribution. You probably note that this internal energy here plus PV, the combination of these two terms here is the enthalpy of the system, the enthalpy H, which is just the internal energy plus PV. Likewise, if you consider all three of these terms here, this is the Gibbs free energy of the system. You could also define the Helmholtz free energy of the system based on this, and that would be the internal energy minus Ts without this plus PV, without the plus PV contribution. That would give you the Helmholtz free energy. So let's now consider what is happening here with the first law of thermodynamics. Now, if we have a system and the system is in contact with its surroundings, what we need to keep track of are the exchanges of the three different types of matter between the system and the surroundings. So we've got some amount of entropy that can be entering the system here, dSE. Likewise, there can be entropy that is entering the surroundings, ds sur. So this reflects the exchange of thermal matter between the system and the surroundings. Likewise, we can have an exchange of mechanical matter, which means that volume can enter the system or volume can enter the surroundings. And there can be an exchange of chemical matter, which means that a certain number of moles of different chemical species are either entering the system or entering the surroundings. And that gives us the dN term. Therefore, using this expression for the change of the internal energy, the change of the internal energy of the system is equal to the thermal contribution to that change. So that's the thermal potential, the temperature, times the change of the thermal matter, the amount of thermal matter, the ds. Then the mechanical contribution is the mechanical potential minus the pressure, times the amount of mechanical matter that is entering the system, dV. And then we have our chemical contribution, which is the chemical potential mu times the amount of each of the chemical species there. And if you have a multi-component system, then the subscripts I are referring to the different types of chemical species, and you'd simply add up all the contributions from each of those chemical species to get the total change of the chemical energy. And so if you add all of these together, with the thermal, mechanical, and chemical contributions. That gives you the total change of the internal energy as a result of the exchange of these three different types of matter between the system and the surroundings. So this equation here is the first law of thermodynamics for the system. You can note that we can write an equivalent expression here for the surroundings that also includes the thermal contribution going into the surroundings, the mechanical contribution, and the chemical contribution. This is a statement of the first law of thermodynamics for the surroundings. It's just taking a different perspective. The equation on the left-hand side is from our usual perspective of that of the system. Normally, it's the system that we want to study, and so we are looking from the perspective of the system. And for the rest of this presentation, we are going to adopt that perspective as looking at this from the perspective of the system. But I want to point out that this equation is, just a perfect analog here for the surroundings, the same exact terms, just coming from the perspective of the surroundings. And this shows that it's actually rather arbitrary about what you define as the system versus the surroundings. In the future, and hopefully in a few weeks, I'll have a video ready that discusses the nature of the surroundings and the fact that it's really arbitrary about what you define as the system versus the surroundings. So please look for that in the near future. But now let's consider this, what we call the modern statement of the first law. Where this is from the perspective of the system, that the change of the internal energy is equal to this change of the thermal energy that is entering the system. And then we've got the change of mechanical energy and the change of chemical energy. We propose this as the modern statement of the first law because it is based on the exchange of these three different types of matter, the thermal matter, mechanical matter, and the chemical matter. It's building upon fundamental thermodynamic quantities, such as these types of matter and their corresponding potentials. And we can write the first law here without defining even what heat or work means. This equation applies to both reversible and irreversible processes. It's easy to extend this to include, say, entropy generation within the system due to irreversible processes, for example. And the other nice thing about this modern statement is that it very naturally applies to both open and closed systems. So for an open system, we have an exchange of chemical matter here, which means that we have a non-zero dn term. For a closed system, this dn term is zero, and we would just be left with the thermal and the mechanical contributions. In this particular lecture, we are going to focus on open systems and cover those in detail. So what I'd like to do next is to look at some more of the details of the exchanges that occur between the system and the surroundings. In this diagram, everything here in this circle represents the system, and the system has its potentials defined. So it has a particular temperature T, it has a pressure P, and it has a chemical potential mu. So the system is within the circle. Outside of the circle, we have our surroundings. The surroundings are defined as just everything that is outside of the system. And we're going to look at the first law of thermodynamics in terms of all the different types of matter that are exchanged between the surroundings and the system. In particular, what are the amounts of thermal matter, mechanical matter, and chemical matter that are entering the system from the surroundings. Now we have three different parts around this circle here that I want to go through. On top, this is the amount of entropy exchange that is due to heat conduction. And we're labeling this as dsq, where this superscript q is meant to indicate heat conduction. So this dsq would be the amount of thermal matter, the amount of entropy that is entering the system from the surroundings, just purely due to heat conduction. If we multiply that by the thermal potential, in other words, multiply that by the temperature, what we get is the amount of heat that is transferred. And if we consider some infinitesimal amount of entropy that is transferred in due to heat conduction, multiply that dsq by T, and that gives us the dq. And so this is one of the types of exchanges that can occur between the surroundings and the system. Uh, the next the next type is on the lower left corner, and this is due to the mechanical work that is operating on by the surroundings on the system. This would be due to either some sort of compression or expansion of the system based on mechanical work operating on it by the surroundings. And so the volume change as a result of that mechanical work is given by dVW, where this W is meant to represent the mechanical work. If you multiply dVW by its mechanical potential minus the pressure, that gives us the total amount of mechanical energy that is resulting from that work, and that is just dW here, this infinitesimal amount of work that results from this infinitesimal change of the volume of the system dV. So dW is equal to minus P dV. So we've got heat conduction and we've got mechanical work. But if this is an open system, the key part for being an open system, of course, is that chemical matter can be exchanged between the system and the surroundings. Now, if we define dN to be the amount of change of the amount of chemical species entering the system from the surroundings, and then multiply that by its corresponding potential. In other words, multiplying by the chemical potential, mu dN would be the amount of chemical energy that is entering the system from the surroundings. Now, the interesting thing about open systems are that the amount of chemical matter enters the system, but that chemical matter is also changing the volume of the system because it takes up space. And so there can be a change of the volume of the system as a result of, say, adding more atoms or more molecules into the system. So if we define the molar volume to be this lowercase v, if you multiply the molar volume by the change of the number of moles, dN, what that gives us is then the volume change that you would expect by adding dN amount of chemical matter. And then multiplying that by its mechanical potential, minus P, that gives you the amount of mechanical energy that is added as a result of the volume change due to adding that chemical species. So that's this minus PV dN. Likewise, the chemical species that enter the system are also carrying thermal energy. And if we define the molar entropy here as the lowercase s, so this would be the entropy per mole, and then multiply that molar entropy by dN, the change of the amount of chemical species, then that gives us the amount of thermal energy that is entering the system as a result of this chemical exchange. Multiplying that by the thermal potential, the temperature, gives us the amount of thermal energy that enters the system as a result of the chemical exchange. So this is what makes the chemical exchange so interesting, that we have not just a change of the number of species, but there is a corresponding change of the volume due to having a certain molar volume of the matter that enters, as well as having a change of the thermal energy of the system because of the molar entropy. So if we look at this, chemical matter carries entropy. That is what is in this upper dashed box here. And chemical matter also carries volume. The amount of entropy is defined by the molar entropy, and the amount of volume is defined by the molar volume. And if you take those intensive quantities, multiply by the change in the amount, the dN, that gives you the total amount of entropy and or volume that is being introduced because of this exchange of chemical matter. And so if we want the total entropy change, we need to consider two contributions to that total entropy change. So ds here, meaning the total change of entropy, has two contributions. It has the entropy change due to heat conduction, this dsq, coming from this upper part, but it also has the entropy that the new chemical matter is bringing into the system. That is this molar entropy here times dN. So we've got the entropy contribution due to heat conduction, plus the entropy that is being carried by the new chemical species. And you need to add both of those terms together to get the total change of the entropy of the system as a result of these exchanges between the system and the surroundings. Likewise, if we want to consider the total amount of volume exchanged or the total change of volume of the system, dV, there are two contributions to that. The first part is just the pure compression or expansion of the mechanical work that is being performed by the surroundings on the system. That is this dVW coming from the lower left-hand side. But then we have the new volume that is being brought by the chemical matter. That's given by the molar volume times the change in the amount of chemical matter. So this lowercase v times dN. We've got, therefore, the two contributions to the total change of volume, and to get them both, we need to add them together. So if we look at this in a bit more detail, let's consider first the two contributions to the change of entropy. The total change in entropy of the system, ds, is the summation of these two contributions. The first term here, dsq, is the change in entropy due to heat conduction. This doesn't involve any change in the total amount of matter. It is just thermal exchange, just purely due to heat conduction between the surroundings and the system. Then we have the second term, which is the change in entropy due to the exchange of chemical matter, this molar entropy times dN. And if we add those together, we get the total change of entropy. Now, taking this total change of entropy, that since the entropy is the amount of thermal matter, to convert that to an energy, we need to multiply by the thermal potential. So in other words, multiply by the temperature of the system. So TdS is the total thermal energy entering the system. And that TdS then has two terms with it. The first term is T times the amount of entropy change due to the heat conduction. This T times the dsq is equal to dq. This is equal to the amount of heat that is being conducted. That is the definition of the heat through heat conduction. So we have our first term is dq. This is the amount of thermal energy that it comes from heat conduction. And then the second term, we just multiply the second term by T, by temperature, and that gives us the temperature of the system times the molar entropy times dN. This is the contribution of the change in thermal energy that comes from the thermal energy that's being carried by the chemical matter. We can rewrite this by taking the common factor of temperature out in front. We can rewrite this as simply the temperature times the summation of these two terms, dsq plus lowercase s times dN. This is just another way of rewriting the same quantity. Therefore, if we want to solve for dq, taking this equation and solving for dq, the thermal energy due to heat conduction, we can solve for dq by taking the total amount of thermal energy, TdS, and then subtracting the Ts dN from both sides of the equation. So the other way that we can write the amount of thermal energy dq is that it's the total amount of thermal energy entering the system minus the contribution that is due to chemical exchange. And then if you take the common factor of T outside, this is T times the quantity ds minus the molar entropy dN. This is just another way of writing the heat conduction part. If we do the same type of analysis here for the two contributions to the change in volume, we see that the total change in volume of the system, dV, has two contributions. The first contribution is the change in volume due to pure compression or expansion. This is just the pure mechanical work that is being done by the surroundings on the system. That is dV with a superscript m here. And then we have another term, so plus lowercase v times dn. This is the molar volume, lowercase v, times dn, the change of the chemical matter. So the change of the number of moles of the chemical species. So the first contribution is the pure mechanical work due to compression or expansion. And then the second term is the amount of volume that is brought by the amount of chemical matter that is entering or leaving the system. Now, if we want to consider the total mechanical work, to convert this to units of entropy, units of energy, we need to multiply this by the mechanical potential. That means multiplying by minus P, minus the pressure. So minus pressure times dV gives us our first term is just dW, the amount of work that is being done by the surroundings on the system. But then the second term is minus P times V dN. So this is the amount of mechanical energy that is being introduced by the chemical matter coming into the system. Likewise, we can take this common factor of minus the pressure here out, and then it's just simply minus the pressure times, then in parentheses, the summation of the volume change due to compression or expansion, plus this volume change due to the exchange of chemical matter. Therefore, we could also solve for the mechanical deformation work, dW, by taking this dW here. We want to solve for this, so what we have to do is add PV to both sides of this equation. So the mechanical deformation work dW is simply the total amount of mechanical work minus P dV, then plus the mechanical energy that is due to the chemical matter exchange, so PV/dN. We can extract this common factor of minus pressure and pull that out in front, so it can be also written as minus pressure times dV minus molar volume times dN. So this is the same thing mathematically that we did with the entropy contributions, now applied to these two contributions to volume exchange. And so when we put all of this together, what we see are that there are many different ways that we can rewrite the first law of thermodynamics. And four of those equivalent ways of writing the first law of thermodynamics are highlighted here in the purple boxes. These are all showing the changes of the internal energy of the system, but they can be expressed in different ways depending upon whether you wish to express it in terms of the exchange of all the three different types of matter, the ds, dv, dn, or you could represent it in terms of dq, taking the place of the heat conduction part of the entropy exchange. You could also use dW, taking the amount of pure mechanical work due to compression or expansion, or you could use a combination of both dQ or dW. So using all of those equations from the previous two slides, these are just four different ways of rewriting the first law of thermodynamics, and I'm putting them all here. So these are four different ways of writing the first law of thermodynamics in terms of this change of the internal energy of the system. Kind of the most natural way, at least for me to write it, is the first one. The first expression, du, is equal to Tds, the thermal contribution, minus PdV, the mechanical contribution, plus mu dN, the chemical contribution. But what we can do is take the thermal matter here, the amount of thermal matter entropy, we can write it as in terms of its two contributions. We could take the dV, write it in terms of its two contributions, and we can basically combine these terms in different ways and write the du, the change in internal energy, in terms of heat conduction, dq, change of the work, dW, or a combination of the two. And the other thing I should note here is that the internal energy of the system, the total internal energy, can also be equivalently written in terms of the Gibbs free energy, the Helmholtz free energy, or the enthalpy. If we do that on a molar basis, this lowercase u is the molar internal energy. This is the amount of internal energy per mole of species, lowercase u. This can be rewritten in terms of the molar entropy, so Ts minus, and then PV, where this lowercase v is the molar volume, and then plus the chemical potential mu. The chemical potential mu is just another way of stating the molar Gibbs free energy or the molar chemical energy of the system. They all mean the same thing. Molar Gibbs free energy, molar chemical energy, and chemical potential all mean exactly the same thing. And so we use the term chemical potential to represent that. Now, if you want to rewrite this in terms of the enthalpy, the molar enthalpy, lowercase h, is simply going to be the internal energy, the molar internal energy, plus the PV contribution. And so if you subtract the PV contribution from both sides, then the molar internal energy is simply the molar enthalpy minus PV. Same thing in defining the molar Helmholtz free energy, which is a lowercase f. The molar Helmholtz free energy is defined as being the internal energy minus temperature times the molar entropy. And so if you add Ts to both sides, then you can rewrite the molar internal energy as simply being the molar Helmholtz free energy plus temperature times the molar entropy. And so using all of these equations, then we can get all these different expressions for the first law. These are all mathematically identical. They all mean exactly the same thing mathematically, exactly the same thing physically. It's really up to you about which form of the first law for open systems that is most convenient, given the problem that you wish to address in the terms in which you wish to describe it. But there are many other ways that you can also write the first law of thermodynamics for open systems. This is extending the four equations from the previous slide now to multi-component systems. In a single component system, we just had mu dn because we only needed to define one chemical potential if there's only one component in the system. If you have multiple components, each one of those chemical components has its own chemical potential, which is now mu sub I, and then we can have an exchange of the number of moles of each one of those different types of chemical species, and that's given by the dn sub I. And then if you add up over all those different types of components, then you get the total amount of the total contribution of the chemical energy that is being exchanged. And so we can take those four equations from the previous slides and easily extend them to multi-component systems just by replacing the mu dn with now a summation going over all the different components of the system using mu sub I as the chemical potential for each component and dn sub I as the amount of chemical exchange of each component. But there's more. We don't necessarily have to express the first law in terms of just du, a change in the internal energy. We can also equivalently express it in terms of a change in the enthalpy of the system, the dH of the system. And here are a couple of different ways to do that. The first equation is using heat conduction dq. The second equation is in terms of the exchange of the different types of matter, the change of entropy, and the change of the potential here, dp, and then the change of the amount of moles of the chemical species here, dn. So this is two equivalent ways for expressing the first law as changes in enthalpy. And we can take those and express them as for multi-component systems by expanding out then the molar enthalpies, H sub I, or the chemical potentials, mu sub I, summing up over all the contributions from based on all the exchanges of the different types of chemical matter, Dn sub I. There's more. You can express this equivalently in terms of changes of Helmholtz free energy, dF. Here are two expressions for the first law of thermodynamics for open systems, now expressed in terms of changes in the Helmholtz free energy. The first two equations here are for single component systems that can easily be extended to multi-component systems here, where now we've got a summation over each of the molar Helmholtz free energies, F sub I, for each of the components, or in terms of the summation over all the different Gibbs free energy contributions based on the chemical potential for each component mu sub I and the exchange of each type of chemical matter. You can also write the first law for open systems in terms of a change of Gibbs free energy. This is actually a very common way to see the first law expressed in material science systems. So the dg, the change of the Gibbs free energy of the system. The first equation here shows it for a single component, and the second equation here is for multi-component systems. Let's walk through a couple of simple examples so you can see how this works. The first simple example is an open system under constant temperature and constant pressure conditions. So let's take our last equation here that we had for the first law written in terms of a change of Gibbs free energy. And if the system is constant temperature, that means that dT is 0 because there's no change of temperature. And if there's no change of pressure, then the dP is 0. So the ds term goes to 0, the dP term goes to 0. These first two terms go to 0. And so if there are if it's a constant temperature system, a constant pressure system, and we assume that there are no internal chemical processes, then the total change of the Gibbs free energy of the system is simply equal to this chemical contribution. So summing up overall the different chemical species, the chemical potential is mu sub I times the change in the amount of each of those chemical species, dN sub I. So this is a very simple case. And one of the things that I will note, just to drive this point home, is that the Gibbs free energy of the system is simply the chemical potential times the number of moles. So it's simply mu times n. As a single component system, it's usually written as just mu times n. For a multi-component system, we have to write it in terms of the summation of mu i's times n sub i's to get the contributions to the Gibbs free energy from each of those components. We can also rewrite that in terms of the mole fraction of each species, x sub I. The mole fraction of each species is simply the n sub I divided by the total n, the total amount of moles of chemical species. So we can rewrite this in equivalent fashion by bringing out the n, the total number of chemical species, the total number of atoms or molecules or moles, and then use x sub I as the mole fraction of each of those components. So the Gibbs free energy is simply chemical potential times n, which means that the chemical potential is simply the molar Gibbs free energy. It is simply the G divided by the n, and therefore the chemical potential of the system can be expressed as this average chemical potential based on averaging over each of the chemical potentials of the individual components weighted by their corresponding mole fractions x sub I. So that is a simple example. Another simple example here is an open system under adiabatic and constant volume conditions. If we have an adiabatic condition, that means that there's no heat transfer between the system and the surroundings. So dq would go to 0. And if it's a constant volume condition, then the dV goes to 0. So the convenient form of the first law in this case would be where the du, the change in internal energy, is expressed then in terms of the dq and the dV, since they both go to 0. And the term that remains is then the summation of these molar enthalpies, H sub I times the dN sub I's. And therefore, this reduces to du is equal to, and then the summation of all the molar enthalpies times the change of the amount of each of the chemical species. Now, there's a subtlety here. And just because the system is constant volume doesn't mean that there's no mechanical work that is being performed. And why is that? We need to look at this in a bit more detail, recalling that there are two contributions to volume change. And so if the total volume change is zero, meaning this minus p dv term is equal to zero, that means that the net volume change is zero. So the net volume deformation of the system needs to basically, there's a certain amount of molar volume that the chemical species are bringing. And so if you have dn chemical species entering the system and the molar volume of the species is this lowercase v, that means that if you have new chemical matter entering the system, it's bringing volume with it. And that means that there needs to be some amount of mechanical work being performed by the surroundings on the system that exactly counteracts that new volume that is coming in from the chemical species. So if you have VDN as being the amount of volume that is brought by that new amount of chemical matter, and we need to satisfy this condition that the volume of the system is a constant, that means that there is a contribution to the mechanical work being performed by the surroundings on the system that exactly cancels that volume change. So that means that there does have to be a net volume deformation just from this mechanical work that's equal to minus VDN to exactly counter the volume change due to the chemical exchange. And therefore, adding these up then gives you that the total amount of volume change is equal to zero. So that is a subtle point. So if you have an open system that's under constant volume conditions, don't just assume that there's no mechanical work being performed. Because if the change of the number of chemical species is changing and the volume is a constant, there has to be some mechanical work performed by the surroundings on the system in order to exactly counteract that change to maintain a constant volume. Or in other words, if you have here this change of the internal energy of the system, and this is under dq equals zero and dv equals zero conditions, we can write this in terms of the contributions here of the molar internal energy times the change of the number of species, plus then the amount of mechanical energy that's being brought by these new species because of the dn contribution. So we've got our pressure times the volume times the dn. This can be rewritten then as the U plus PV times dN, and this molar internal energy plus pressure times the molar volume. This, of course, is simply the molar enthalpy, and that's how you get the molar enthalpy here in this equation. So for a single component system, it's HDN. For a multi-component system, we have to add up the molar enthalpies for each component I multiplied by the change of the amount of chemical matter dN sub I. So that brings us to the end of this lecture. To summarize, I want to put all of these equations here on one slide. There are all these equivalent expressions for the first law of thermodynamics for open systems. This slide shows the 9 different equations that I showed in this presentation for single component open systems. The first 4 on the left here are written in terms of the change of the internal energy. Then we have 2 expressions here written in terms of the change of enthalpy, 2 expressions in terms of the change of the Helmholtz free energy, and then this final expression written in terms of the change of Gibbs free energy. These are all 9 equivalent expressions. They all mean mathematically the same thing. The ones that you should use are based on the conditions under which your system is being studied. So choose the expression that is most convenient for you to study. This slide shows the expressions for single component systems. For multi-component systems, these are all simple extensions where we're just summing over all the different contributions to the exchange of chemical matter for each of the different contributions here. I equals 1 all the way through little n, the total number of different components here. And so these are 9 expressions for the first law of thermodynamics for open systems that are now multi-component. So everything on this slide is for multi-component systems. Everything on the previous slide is for single component systems. I hope you enjoyed this lecture. I hope that this showed you how we can express the first law of thermodynamics for open systems in a way that is kind of more intuitive compared to the traditional approach, while also showing you that there are many different equivalent ways of writing this. Each of them may be useful depending upon the situation that you find yourself for your particular study. I showed you a couple of simple examples. There are actually quite a few more examples um, showing the utility of the first law of thermodynamics for open systems in this paper that is published in MRS Bulletin. So you can look this up if you go to Google Scholar and just put in that title. You can get a copy of this paper. And of course, also check out Dr. Chen's textbook. So thank you very much for your time. The next lecture is going to be about the nature of the surroundings in thermodynamics. So I hope that you'll come back to watch that one as well. So thank you very much. If you have any comments, please feel free to leave them below.